So it's a great pleasure to introduce today's speaker, Felipe Gonçalves from IMPA. This is the first PD seminar of the 2024. And Felipe is going to talk about Fourier's summation formulas and quasicrystals. Okay, go ahead.
Okay. Thank you, Felipe, for the introduction. So the goal of these 3 lectures is sort of in a way, we'll try to explain the things I've learned so far, looking at this field. It's very connected with physics, especially crystallography, so the study of crystals and objects and substances via X-ray crystallography. And so the goal is to understand a little bit of the physics side, but also then eventually to dig into the mathematics behind it. And the objective, the final one, is like to show some recent results I did in this field and sort of also lay out the techniques and background you need to understand the results. And in the last 2 lectures, I would try to really dig into the mathematics, and so they'll be more technical. But this first one is sort of an expository lecture from the historical background to what we have nowadays. Okay. So this is the idea. So the first thing you need to understand is what's the Fourier transform of something. And so in this talk, I'll use this definition of Fourier transform with the 2 pi I. The people that don't like to put the 2 pi I here, I do. And especially the Fourier transform of a measure. So I'll give you a measure, which is going to be, say, a complex measure on the Euclidean space, n-dimensional Euclidean space. And you can associate the Fourier transform by this, okay? And here, dot here will be the inner product between 2 vectors. Okay, so a simple example would be a measure that has some absolutely continuous part, like a Gaussian, and plus some singular part, say a delta at some point. So these are the kind of measures we'll be looking at. So for instance, here, the Fourier transform with this normalization here gives another Gaussian plus just an exponential evaluated at lambda. If you put a delta here, just going to evaluate c at lambda and get this exponential. Okay. Okay. So as I said, in this talk, what you have to think about as a measure having some absolutely continuous part and maybe some singular part. Okay, and the singular part can be further divided in 2 bits, but for this series of lectures, you can just imagine that the singular part is just what we call pure point. So it's just a sum of deltas at some points lambda, and it should be lambda k here, and lambda k is just a set of points in Rn. Okay. Oh, and then a of lambda k. Oh, my tech here is not good. A of lambda k should just be a sequence of coefficients. Okay, so that's what you have to imagine: a continuous, absolute continuous part maybe, and a singular part. And so if you take Fourier transform here, it's just a Fourier transform of this function plus some limit. Perhaps this converges, perhaps it doesn't. It depends on the measure. Okay, and so one thing you can do is try to compute Fourier transform of measures which are pure point. So the classical case, like this is like 100 years old or more, is Poisson summation formula. Okay, so what is Poisson summation formula? So you look at this measure here. Mu equals the sum of deltas. Okay, so over the integers. So it's just a set of points, deltas of weight 1, and they're supported in each integer. Okay, so if you try to compute this Fourier transform, which is going to be the limit of this sum, since it's a symmetric sum, you can show that's just the limit of this thing. What you can do is you can plot this function here for different values of t. So here is a plot for t equals 10. And what you see, it still is a one periodic function because we have cosines here of 2 pi k. But it has some spikes. And the spikes are exactly at the integers. Yeah? Of course, if you put c equals an integer, you get just 1 on the right-hand side here. So you get 1 plus 2 times 10, so you get 21. That's why you have a height of 21 here. And these peaks are not sort of the same just because of some numerical errors in the computation of the plot. Okay, but they should all be equal to 21. You can do the same with 100. It's a bit more complicated because to plot this, you can't just plot in a naive way. You have to plot it in a sort of a clever way to see the picture. But you can see still that the peaks are accumulating at the integers. So these are the integers 0, minus 1, 1, 2, minus 2, etc. Again. So what you can show is that in the limit, what you get is the sum of deltas again, and at the integers. And so you can show that what you get in the end is the same measure again. So the deltas with weight 1, you compute its Fourier transform. It's again a pure point measure, that is just a sum of deltas, and it agrees with the initial measure. So this kind of measures are called a measure which Fourier transform equals itself. It's called self-dual. And this is an example of a pure point measure, which is also self-dual. It's more than just pure point because the support of the measure, which the integers here, they are spaced. There is a separation between the points. Okay. So this is sort of the background, the mathematical background to understand what's going on in the physics part of this talk. There's one more piece that I would like to talk about, which is the extension of this thing that I just mentioned to higher dimensions. So if I give you a lattice, so a lattice here will be a full rank discrete lattice. So imagine that is just some non-singular matrix A times the integers. Okay, so this be a collection of points, a periodic collection of points on Rn, which is the image over some non-singular linear transformation of the integers. Okay, the dual is just when you do the same with the inverse transpose. Okay, so a nice example is the triangular lattice. So the triangular lattice would be the points in the intersection of these infinite lines here. So you have this point here, that point there, this point here, and this point there, and so on. And you can try to compute its dual. Its dual is going to be the hexagonal lattice you see here. So the corners of the hexagonals you see here, plus the centers. Okay, this is also a lattice. It will be the dual of this lattice. So whenever you get a lattice, you also get a dual. And in this way, Poisson summation also extends. What you can show is that if you consider this measure here with just deltas with weight 1 centered at the points of the lattice. So for instance, this guy here, so this point here, for instance, you put deltas of weight 1 here. You can try to compute this Fourier transform. What you see on the other side is essentially just the sum of deltas with equal weights in the dual lattice. And there is a scaling factor here, which is the determinant of the matrix. But anyway, it's going to be equal weights on all sides. So this is called classical Poisson summation. And this formula, this identity here, is sort of a written from a distributional point of view. But if you want to just look at in the sense of a identity, say a Fourier summation identity, this would be the identity. You get some test function phi, you compute this sum with the Fourier transform. What you get on the right hand side, you get just the function phi evaluated at the dual. Okay, so this identity here and this other one, these are equivalent. Okay. And you can show that this is a generic statement. If I give you two measures, mu and nu, to say that the Fourier transform of mu equals nu is the same as to say that you have such identity for every test function. Okay. So this will be important later on. Okay. So now let's talk about the physics of it. So I want to talk about crystallography in particular. So let me read this. It's a long sentence. Let's read together. So it's a branch of science that wants to understand bonding of atoms and also their geometric structure, how they are distributed. And you want to not only understand local structures, but the average local structure in some substance or some material, say. And so classically, understanding the structure of some material or some, say, metal alloy or something like that is important in chemistry for identifying substances. But in modern days, people are using X-ray crystallography and etc. To access what's the atomic structure of certain things, even in more macro structures like DNA and proteins. People use techniques from crystallography to understand their geometrical properties and so on. So what's the setup? This is very simple, and by the way, I'm not an expert in the physics part, so take everything I say with a grain of salt. But so usually what you have is some sort of an X-ray beam, and you have a sample that you want to analyze. You shoot that X-ray in the sample, and you get some diffraction pattern. Okay. There is another one which is using electrons. So you shoot electrons in the sample. They will bounce around the sample, and then you will come out in a detector, and you also get a diffraction pattern. Okay. There are a bunch of other methods. This is just two that are most used. And so for instance, this is an interesting thing, which is that tantalum pentaoxide. I'm not a chemist, but I never heard about tantalum before looking at these things. But in any case, it's a sort of a typical example people give. There is a typo here. Typical example people give of a substance that has a periodic diffraction pattern, and this is the diffraction of the tantalum pentaoxide that you see. So you do. So this is electron diffraction. So you bombard the substance, which in this case is just a powder, like that, and you with electrons they scatter around. Then they bounce in a screen, and there is a contrast you have to do, and then finally you get this picture, and you see a bunch of spots with different intensities. Of course, that you have different intensities because the beam is focused in a central point, which is this one, and so once you get away from the beam, you get less intensity. But you can clearly see from here that it's a periodic structure. At least you see a periodic diffraction pattern. Okay. And one thing you have to understand is that if I will have to write this because I think it's not in the next slide. If mu represents the substance, what you see in the diffraction pattern is the Fourier transform, but only, say, the amplitudes. You lose phase information because you take the absolute value here. Okay, it's actually squared. Okay, so what you see here is the Fourier transform of your substance, but sort of an average out, because this is sort of the average, is the Fourier transform of the average geometrical structure of your substance. Okay. But then you get something periodic. Okay, you have so at least you know that the support of this measure, the Fourier transform, is periodic, and then from this you can infer that the atomic structure of this substance, the tantalum pentoxide, is indeed a periodic structure. Okay, on average. Okay. However, this is not the case for some other substances. And this is the electron diffraction pattern of this alloy, aluminium, magnesium, zinc. This is just like a photo of the thing. It's just shaped in a, I don't know, it's just shaped in a nice geometrical shape so you can observe. But this is the electron diffraction pattern you see. And from here you see already some different things, because what you see, for instance, how many points you have here? You have 1, 2, 3, 4, 5, 6, 7, 8, 9. You see sort of a tenfold symmetry. We see pentagons. Yeah, and you see pentagons here. For instance, there is a pentagon here. So at least here you have a 5-fold symmetry. Okay, and what you can show is that this is sort of a forbidden symmetry, which means that this structure here, this diffraction pattern you see, is not periodic, in the sense that if you take the picture and translate it and try to fit back again in the picture, you can't do it. Okay? That tells you that there is a problem with this structure here, because the average geometric atomic structure of this substance is in a way aperiodic as well. Okay? And so the local structure, say, if you zoom in the atomic structure here at some point, and you determine what it is, and then you go to some other place of the substance, maybe it's totally different, or arranged in a different way. Okay? And so this was discovered in, I think, in 1986 by a guy, which I will show in a moment. Oh, yeah, I will show the picture in a moment. So this is another diffraction pattern. I think this is just, it's just a high-resolution picture of a part of this meteorite. It's called decagonite. It's also a famous one. And you see this very weird pattern. Okay.
The numbers 71, 24, and 5 is related to atomic weight or to...
Yeah, this is atomic weight. Yes.
It's atomic weight.
Yeah. So, as far as understood, what you have to do to get these things, usually it has to be some aluminum alloy, and you have to sort of heat it up pretty high and then freeze it super fast. And then you get this sort of things.
What should be the proportion of atoms?
This is another one which I like, which is from another aluminum alloy with like 14% of iron and etc. So this again is the diffraction pattern. And what you can do, so you have the substance. What you can do is you can start rotating the substance. Okay? And so, and here, suppose the substance is like that, then what you can do is you can rotate like 31 degrees in this direction, 37 or 63 or 90 degrees, and then 18 degrees in this one, and then maybe 32 degrees in the other direction, and so on. And so you get different pictures. And these ones, especially these ones, I think, this one, and this one, they're called one-dimensional quasicrystals, because you see something like, I think this guy here, you see in this direction periodicity, but in this direction you don't. And also I think, this guy as well. You see in this direction periodicity, and in this direction you don't. And so these are called one-dimensional quasicrystals. And so people study these things as well. Okay. And this is another example of another aluminum alloy. And this is this is a picture of a slide that Roger Penrose presented in one of his talks, sort of explaining why when you see five-fold symmetry, that's what we see, five-fold, ten-fold, or anything other than 1, 2, 3, 4, or six-fold symmetry, necessarily what you see is an aperiodic thing. And it's a very nice proof. So imagine that you have 2 points. Will be, say, 2 points in this thing here. And suppose they're as close as possible. And suppose that the thing has n-fold symmetry. So if it had one-fold symmetry, you don't do anything. If you had two-fold symmetry, then what you do is you rotate this point with this one fixed, and then you get this guy. And you rotate this point here with this other one fixed, and then you get that guy there. Okay, then you obtain 2 points which were not closer than the initial 2 points. Okay, so you're assuming that the initial 2 points you got was 2 points which are closest as possible. Okay, and with three-fold symmetry again, four-fold symmetry again, you don't get points which are closer than before. And with six-fold symmetry, which is not here, you also don't get points which are closer than before. But you do get with five-fold and any other n-fold symmetry. You just have to rotate enough, and then from 2 points, which supposedly closest as possible, you would get 2 other points which are closest as possible. So that would imply, so that would be a contradiction, then that would imply you don't have a periodicity. Okay. So the only rotational symmetries you have in crystallography are those of like periodic structures are those here. Okay. So this is a nice proof. It's sort of a pseudo argument, but you can formalize it. And so all the pictures we saw, they represent what is called physical quasicrystals. There is a mathematic definition of quasicrystal, which I will get later. But the physical quasicrystal is some quasi-periodic crystal. It's a structure that is ordered, but is not periodic. Okay, and so sometimes they're called quasi-crystalline patterns, and it has to be some sort of a structure that can fill the space, but it lacks translational symmetry in any possible direction. Okay, so it's not periodic at all. Okay, as I was saying, the only things allowed for the classical periodic case is 1, 2, 3, 4, or 6 rotational symmetry. And usually when you see five-fold symmetry, what people call it the forbidden symmetry, it tells you that it's non-periodic. So this is a physical quasicrystal. And I think the term was given later, but the guy who discovered this is this guy here, Duns Skeachman. He was the first guy to find these structures, and I think several years later, I think maybe less than 20 years, 25 years later, he got the Nobel Prize in chemistry. And at the time, people were like not believing his results, saying that he did wrong experiments. But then some years later, people redid the experiments and yeah, these things really exist in nature. Okay. And one of the reasons that several physicists were skeptical about this, which I will say in a moment, is due to the sort of a high-dimensional nature of the thing. The models that describe these quasicrystals, they come from high-dimensional models. So you sort of get a model in say 10 dimensions in space. You get a projection, and you get this 2-dimensional picture. And at the time, the physicists were sort of no, it's impossible. Nature doesn't behave like it has more dimensions. That was one of the main arguments. And let's say it's and what happened is that Roger Penrose came up with which is called the Penrose tilings now, very famous Penrose tilings. And this is another picture. And if you look at this picture, say especially this thing here, and you look at this guy here, this guy here, they look remarkably similar. And indeed, there is a certain aluminum alloy that fits exactly this thing. Like the peaks you see, which are called Bragg peaks in the diffraction patterns you see, they match exactly the points in this thing. Okay, and so that was another very amazing thing that happened at those days. This is Roger Penrose. He also won the Nobel Prize, but it was for his contributions in black holes theory, etc. And he's standing on the Penrose tiling as well. And yeah, so what is shown? So nowadays there is a standard way of creating models to explain these quasicrystals, and they come from this cut and project model sets. So suppose you get a lattice in some high dimension. So suppose this ambient dimension here is, say, dimension 5. Okay? And then what you do, you get what is called a window, say, in 3-dimensional space. So suppose this is 3-dimensional and this is 2-dimensional. And you get a window in 3-dimensional space. Okay? And you look at the points of the lattice whose projection in this direction fall inside this window. So it will be this band here of points. And then once you have fixed those points, you project in the other direction. Okay? Then you get this little points here, this little open points below here. So this is what's called a cut and project. I cut the band, so I cut this gray band here, and I project down. Okay? And so then Cohen showed that you can generate the Penrose tiling from a projection from a 5-dimensional space. Okay? It's sort of you just take the Z5 lattice, you make a small translation, and you project with using a window which is sort of a cube. Okay? And this is the standard model. Remember I told you the Penrose tiling fits exactly some of these diffraction patterns we see in these quasicrystals, these physical quasicrystals. And so nowadays this is like theoretical physicists study this a lot, like how to create models to explain the pictures they see. And also this was mainly this cut and project and model sets. It's mainly contributions of Yves Meyer, and so but at the time it was one of the arguments that people were using that the experiments should be false and things shouldn't work this way because physics cannot come from high-dimensional space. Like how the hell you can see a crystal which has an image that comes from a 5-dimensional projection? So that was the main argument at the time. But nowadays it's standard physics. Another point that I would like to stress. So this is the first thing I say. If mu represents the substance, so perhaps this slide should be before this, at the beginning. So if mu represents the substance, so the support of mu is sort of a uniformly discrete because so mu represents the average structure of the substance, of the metal alloy, etc. And atoms cannot be arbitrarily close together. So uniformly discrete means that there is a minimum separation between points. They cannot get as close as something. And so any natural substance would have this property. It would be uniformly discrete. Okay. And so the diffraction pattern we see is like a combination of deltas, so they call Dirac comps. And the intensities you see are called the Bragg peaks in the pictures you see. And if essentially it represents me, the Fourier transform of the measure squared. But you lose phase information again. So there is a big area which is called phase retrieval. That there is even a mathematical area here that people that actually works in mathematical phase retrieval things and methods and algorithms to how you can say take multiple samples of your substance, and so you get different. So you see the substance say from different angles, but you're always measuring only the absolute norm squared of the Fourier transform, and then from all that data, you have to recover the atomic structure. And there are a bunch of methods to do these kind of things. They're called phase retrieval. But one thing I want to stress is that the real world quasicrystals, although the pictures we see look like, so if you look at this diffraction here, say this guy here, it looks like that the points sort of have a minimal separation. This is just an artifact of the experiment, actually. What happens is that the black parts we see here is just because you can only see, say, 10 to the minus 4 of the intensity of the brightest peak. So if it's below some threshold, you don't see it. Doesn't mean it's not there. Okay? And from the models you have from cut and project sets, people know that this thing, if you had the power to go all the way down to 0 intensity, you would see just everything white. Okay? But you don't, because you have a cutoff. Okay? So it's supposed to be everywhere dense, the support of mu. So what I'm saying is that from the physics point of view, it would be interesting to study measures, pure point support, pure point spectrum, such that the support of mu is dense. Okay, from the physics point of view, it would be interesting to study those kind of measures. Okay. Okay, so let's go back where I was. Yes, and I think the final point I want to stress is that yes, that was the thing I was mentioning, that we sort of only see we see a cutoff, and so we don't see the full support of the measure, although from the most models we know that the support has to be dense. Okay, I mean, can we prove actually experimentally that the support is dense? Of course not. I mean, there is a limit. And if you go to the Planck scale, you can prove that something is closer than that. But it's from the models, from the cut and project models, we know that the support has to be dense. And so, what are the main open questions that after all this introduction, what are the sort of questions that would be obviously interesting to be solved, interesting to study, say? I think the first one is like, I give you a measure, mu, it's pure point, and a computed Fourier transform is also pure point, so it has pure point spectrum. And I want to know, like, what kind of measures can be of this form. That would be the first main classification question you would like to ask. And then, from the physics point of view, like, which of those correspond to the things we see in nature? Which of those correspond to the pictures I just presented to you? And the third question would be, more from the mathematical point of view, is that if I sort of impose a bunch of conditions on my measure mu. Oh, it has to be of this way. Oh, there is this geometric property about measure that I know. So what I can infer about this Fourier transform, and vice versa. If I impose certain conditions on mu hat, what can be inferred about mu? So that would be the more mathematical point of view. Okay. So the idea is to sort of answer the first question completely. So the idea in this, in the final talk, is to sort of answer the first question completely. What kind of measures like this can exist? Okay. Any questions so far? Okay. So I think now we get to the mathematical side. Okay. So enough about physics, the stuff I don't know. Let's talk about the stuff I do know. And so let's start to make some definitions. So from the mathematics point of view, many mathematicians have wondered what kind of geometric properties can we impose on the spectrum and the support of the measures so I can classify how the measure looks like. Okay? And so one thing that people were interested was in crystalline measures. Sometimes they are called quasicrystals, Fourier quasicrystals, doubly sparse, quasicrystalline. There's a bunch of names, depends on the author, depends on the K conditions, depends if you're from physics or if you're from mathematics. There's no agreement, and people actually like to fight about their definitions. Okay? And so I will stick with Yves Meyer's definition, which I know is not a good one. It shouldn't use this name, but it's stuck. So I'll keep using his definition. I don't have a good name. So I would say that a measure is crystalline if mu is the sum of deltas for some points, and this set of points is locally finite, and the Fourier transform has the same property. It's the sum of deltas supported in a set of points, and the set of points is locally finite. What do I mean by locally finite? By locally finite means that I get to any bounded open set, there's a finite number of points inside. Okay? In particular, points cannot accumulate. However, they can get pretty close to each other as long as they zip to infinity. Okay? It's not a good name because crystalline, it's implicit that comes from real world quasicrystals or crystals, but they usually, if it's a quasicrystal, usually the Fourier transform has dense support. And so asking that it's locally finite automatically makes this not interesting to physics. Okay? But it is interesting to mathematics, especially from the number theory point of view. And I will try to convey that in the other talks, not in this one. Okay, so let's start with some examples. So the first example is Poisson summation that I explained to you. But you also have a nice example for Guinand from 1959. Although he says in his paper that he took this example for Landau from a book of Landau from 1909. And if you go in Landau's book, he says he got it from some other place. And so it could be even older. But in any case, he constructs a measure, mu, which is equal to its Fourier transform, but it's given by this. Okay? It's not supported anymore at the integers, but square root of integers plus 1 over 9. Okay? And the coefficients are those here. Okay? In particular, it's a weird measure because it doesn't have a delta at the origin. Okay? It has a gap at the origin. Okay? And there's another, so what happens is that Guinand didn't realize that his construction came from some other place. He defined in a different way. And if you have the right point of view, you can actually make a one-parameter family of measures like this, n plus c, where c here can be any real number you like, greater or equal than 0. In particular, if you take square root of 2, which will be interesting later on, you get these coefficients here for c equals square root of 2. Okay? And the coefficients bn are just the coefficients of this expansion here. So the first one, b0 would be 1, b1 would be minus 24 square root of 2 plus 2, b2 would be minus 36 square root of 2 plus 288, and so on. Okay? But what I'm saying is that you can actually, for every c, come up with some coefficients, write a measure like that, equals its Fourier transform. You will have some coefficients. It won't be equal to those one. It will be a bit different. But you can embed this in a family. Okay? The nice thing is that if you, in this family, if you put c equals 0, you get Poisson summation. And if you put c equals 1 over 9, you get Guénon's example. Okay? So we will see this family in the other lectures. Okay. And now we sort of are coming into, let me see. Yes, so now I will try to explain what people have done in this area and from a mathematical point of view. But I will need some definitions. So we say that a measure mu is strongly tempered if it integrates a polynomial. Okay, so in this case, it integrates for some n here, and the absolute. I mean, this notation here means the total variation of the measure. Okay, so here is a measure on the real line, and I will try to focus. Yes, I didn't say, but I should say now that I will focus only on the one-dimensional case from now on. Okay. And so this is the definition of strongly tempered, which means that I can integrate any tempered distribution. I mean, I can integrate any Schwartz function against the measure because it integrates a polynomial. Okay. We'll say that function a from the real line to the complex number is locally summable if the support, which would be the lambda such that a lambda is not 0, that should be not 0, sorry, is countable. Okay, and if you, for some enumeration, this is always finite. So if I do local sums, I always get something finite. Okay, so for instance, you can imagine, I don't know, a function which is supported at the points 1 over k for k greater or equal than 1, and you put the value that you want so that this works. Okay, that's one example. Or it could be a function supported on the rationals. You just enumerate the rationals, qn, say, and a at the point qn is just 1 over n squared. So this works. Okay. And then this would be the main definition we're using. So that is, if I give you a pair, which would be a measure, mu, which is strongly tempered, and a by definition has to be a function which is locally summable. So I will call this a Fourier summation pair if I have this identity for every test function. Okay. What this identity is saying that the Fourier transform of mu is equal to a sum of deltas at a lambda delta of lambda by that lemma that I showed before. Yes, I even wrote here. The mu hat, this is saying just that the mu hat equals this sum. In some sense, the correct sense would be that mu defines a tempered distribution. So you can take its Fourier transform, and if you restrict it, the Fourier transform to compactly supported Schwartz function, then it agrees with the measure on the right. That would be an alternative definition. I prefer to think in terms of summation identities than in terms of distributions. Okay. So the first breakthrough happened in, say, now we say 90, probably even 10 years ago. Probably the paper was in the archive in 2014 or something. Which was a paper of Lev and Olevsky. Lev here is, and both of these guys are big names in this area, in the mathematical part, of course. So let me define things first. So I will denote this class of Fs pairs, uniformly discrete Poisson summation, UDPS. It will be the set of Fs pairs such that you can write the measure mu of this form. Okay, what is this form? So forget the n. Assuming n equals 1, capital N here, for instance. It's just I'm summating over a periodic set, alpha z, and I translate by theta j. So this will be the deltas. And I'm weighting. So the weight here is just some trigonometric polynomial evaluated at lambda. Okay, so it's sort of is Poisson summation, because this set here also creates Poisson summation, but it's weighted. It's weighted by a trigonometric polynomial. And for me, a trigonometric polynomial should say this. A trig polynomial is just a sum of 2 pi I, say, theta n x. And the thetas here are real. Okay? A trigonometric polynomial is just a sum with some coefficients. It's just a sum like that, for which these guys here, the exponents here, they're real. Okay, I'm not allowing complex coefficients. Okay, so this is the set. So it's uniformly discrete because since you're considering only a finite number of translations of the set alpha z, you can't have 2 points getting too close to each other. Okay, so the points will have to have a separation, a minimal separation. You could do a sum like that where you allow the alpha to change, but if the alpha changes, then there might be the case that the points are getting close together. Okay, especially if there is 2 alphas, which the ratio is irrational, for instance. So I'm defining like that. And so the breakthrough was, so suppose that mu A is a strong Fs pair. Strong here is just informally means that I'm asking that both mu and A integrate polynomials. Okay? That's what I'm asking. So if the supports of mu and A, okay, they are uniformly discrete, that is, mu is supporting a bunch of deltas, they have a separation. And A, it's a function for each the support, which would be the set, I define it here. The support is this guy. The set of lambdas for each is non-zero. This set is uniformly discrete, which means it's just a sequence of points which has a minimal separation. If that's the case, then mu has to have this form. Okay, so this is a classification result. The only measures that have this form, I mean, if mu has this form, then you can show that A also has this form. Okay. If you interpret A as a measure as a sum of deltas, of course. And so they are saying that this is the only case. So this is a classification in terms of the geometry of the supports of mu and the Fourier transform. Okay. So in a sense, this is not interesting to physics because, as I said, A would have dense support, but here is uniformly discrete. But from mathematics point of view, it's nice, especially from number theory. And the theorem is sharp because of Guinan's example. Remember that Guinan's example was supported in square root of n plus 1 over 9. The difference between 2 consecutive elements, say n plus 1 plus 1 over 9, square root, minus square root of n plus 1 over 9. The difference is decaying like 1 over square root of n. Okay, just take the derivative, for instance. So the points are getting closer and closer to each other. So there is no uniform separation between the points. Okay, so they're saying that if you don't ask that, then you have measures different from those, because Guinan's measure is not like this. So the theorem is sharp. What happens in this case is a funny story. So they didn't know Ginan's paper to show that the theorem was sharp. They wrote a paper. I think it was published in the Journal of Ibero-Mathematics. Yeah, Ibero-Americana. Then Yves Meyer knew the paper, just wrote a short note saying, no, there is this example like 50 years ago. In any case, I think they didn't know the Ginan's paper, so that's why. But in any case, their result is very nice. There was a second breakthrough, and they happened really recently, like in 2020. There's a paper of Kurasov and Sarnak. They were trying to study some other thing, which I think related to quantum graphs. And they end up coming with this construction. So the question is, what are the kinds of measures with locally finite support and locally finite spectrum can exist? Okay? And they were trying to answer this. And in a way, you get a complete answer if you assume that the weights of your measure are natural numbers. Okay? If your weights are natural numbers, this is a complete classification. So let's try to read that. So suppose I give you a polynomial Q, which is a trigonometric polynomial, like that, and assume it only has real zeros, and mu of gamma, so the zeros will be gamma, and mu of gamma is the multiplicity of the zero. So it's a trig polynomial like that, and assume it only has real zeros. That means that if I put x to be a complex variable, I never get a zero. I only get if I put here a real variable. Okay. Then they show that the support of the Fourier transform is locally finite. That means they have an explicit formula that I don't want to write, but its expansion is a sum of deltas supported at some nodes, and this node is locally finite. It's on the real line, so it means that in any interval, there's only a finite number of points. Okay. You can even measure how many points there is in any interval. They have a formula. And then there was, just shortly after, Olevsky and Ulanovsky wrote this, say the converse of this, that if you have any strong FS pair, and you assume that the support of mu and the support of A are both locally finite, and that mu is z-valued, so you only have integers as weights, then it has to be of this form. It means that there is a trigonometric polynomial with only real zeros that matches this thing. So it has to come from this object. Okay? Any questions here? Okay, so then we have these two results. And what can we do about it? So there was another paper, very recent. I think it was like July last year. They proved something. So I sort of lied here. You can only state both of these results in such a way using this paper here. So Sarnak's result was stated not in terms of this thing, but in terms of Lie-Yang polynomials. So let's see what are those. So that's what I was saying. So a polynomial P, complex variables, n-dimensional, is said to be a Lie-Yang polynomial if it never vanishes when all the variables are less than 1 in absolute value, or all the variables are greater than 1 in absolute value. So if z1 up to zn, they all have absolute value less than 1, it's not 0. And the same is for if they all have absolute value greater than 1. So this is called a Lie-Yang polynomial. There are other names for this. They call us, sometimes they're called stable polynomials. a typical example is this one. There are other ways of generating those guys. But you just take a unitary matrix, U, and you add a diagonal matrix with exponentials. Oh, this is wrong. It should be a diagonal matrix. It should be a diagonal matrix with Z1, Z2, not the exponential, sorry, Zn. Should be a diagonal matrix with Z1 up to Zn. Then if all the Z1s have moduli less than 1, this can never be 0 because the determinant of a unitary matrix minus. And if all are bigger than 1, also not, okay, in absolute value. So this is a Lie Young polynomial. But there are ways of generating these polynomials using, from the combinatorics point of view, which is using matroids and etc. But anyways, so they prove the following. If Q is a trig polynomial with only real zeros, it has to come from a restriction of a Lie Young polynomial. And of course, any guy like that has only real zeros by the defining property of the Lie Young polynomials. Okay? And so it's only using their result that you can state the previous two, okay, as a classification result. Okay, so almost finishing. Now what I just want to do is make this remark and then prepare to state the result that I mentioned in the beginning of the lecture, which is this classification result I put on archive last December. But we need some preparatory, so I think in 10 minutes we can finish. Okay, so just a comment here. So one of the nice things that they do was to show that if you get a trigonometric polynomial with only real zeros, so then you can ask, well, how the zeros are separated? Okay, so generically what happens is that they are very non-periodic. Okay, in what sense? Well, if they contain an arithmetic progression, then you might say, well, they have some kind of a periodicity. At least there is a subset that contains an arithmetic progression. Or perhaps if they intersect an infinite arithmetic progression and infinite in an infinite set, then you could say also that's sort of a periodic. No. So generically, what happens is that if you get the zeros of a trigonometric polynomial with only real zeros, and you try to intersect with an infinite arithmetic progression, the intersection is finite. And this happens for any infinite arithmetic progression. So in a way, they are very non-periodic. And this was sort of a feature that people were asking at the time. If given given Lev's result, which was the uniform discrete support and a spectrum, if I break that, if I get, say, trig polynomials, which the zeros can be closed, can I create other measures? And it's sort of a answer, yes. You can create measures that have a very non-periodic support in a way. But again, they missed Ginen's example. So if you go back to Ginen's in 1959, if you look at it the right way, and you embed Ginen's example in a one-parameter family, as I mentioned, then whenever you take C irrational, then this set hits an infinite arithmetic progression at most twice. It can't even hit 3 times. If you hit 3 times, it means that C is rational. It's a nice exercise to show that if this set hits an infinite arithmetic progression 3 times, then C must be rational. It's a boring computation, but you have to square everything, etc. But you can do it. Okay. So again, they missed, in a way. I mean, Ginen didn't do that. Okay, it's my example, but in a way, they sort of missed this thing again. People missed Ginen's paper again. Okay, so now let's prepare for the result I want to state. It's going to be a big term, but just stick with me. So we say that a function, a holomorphic function from the upper half plane, so this is just the upper half plane, imaginary part positive, is almost periodic if you, for any strip, so let me go here. You look at, so this is the upper half plane, and this is a strip. Say this is beta, imaginary equals beta, imaginary equals alpha. Okay, so you look at some strip and I give you some epsilon. There will be some set tau, which is relatively dense. I will say what's relatively dense in a moment, such that f of z is very close to the translation of f by t for any t in this set. Okay, so you get your function, translate a little bit for some t in this set, and you get very close to the function. So for any epsilon, for any alpha and beta, there will be a set tau such that this property is satisfied. And relatively dense just means that there will be a set which is relatively dense on the line. Just means that for any interval of size L, there will be some number L, such that for any interval of size L, there is a point on the set inside this interval. So you fix a length, and you vary this length over the line, you always see a point of your set for some length. Okay, that's relatively dense. Okay, so that's the definition of being almost periodic. So this was defined by Bohr and by a study a lot by Bezikovich, like in the 20s and in the 40s and 50s. And another one that I think that I need is this thing. A function is bounded type. I think a function would be bounded if it's bounded, of course. But if it's bounded type, it means that it can be written as the ratio of two bounded functions. So it's sort of a bounded. It's bounded type. Okay, that's the idea. So if g can be written as a function as a ratio of two functions, then we call it bounded type. Okay, we need two other definitions, and then we can state the theorem. So we say that a function is antipodal if a of minus lambda is just bar of a. We say that an FS pair is real antipodal if mu is real valued, so it only has real values. So for instance, if mu is the sum of deltas, the coefficients are always real. And a is antipodal. And it has to be, because if mu is real, you can show that a has to be antipodal. And so we will say that this pair is real antipodal. And we need that because we have to always split. So if I give you any arbitrary FS pair, mu a, then we can always write this, a1 equals this, a2 equals that. And you separate mu into the real part and imaginary part. So you can show that mu j and aj, they are FS pairs. So you can now, given one pair, you can always split in two, where the measure in each one is real valued. Okay, that would be important. And finally, we need these two things. First thing, we will say that a function which is locally summable has exponential growth if for some c, this sum is finite. So this is essentially an overkill. Most cases, I mean most papers, people assume that a lambda divided by lambda to the k for some k converges. I'm just assuming that they have exponential. And we define this the degree, which is the infimum of this n's. For instance, I would be interested when I can put n equals 2 here. That is, mu integrates 1 over t squared. And this is the theorem. So suppose mu a is a real antipode FS pair. So you have the Poisson summation. Mu is something on the left, a is something on the right. Mu integrates against Fourier transform. A is just a sum of the function. And then we're going to make two assumptions. One, that the degree is less or equal than 2. And that really is an assumption. And then this thing is not really an assumption, because the exponential growth is really a weak, very weak assumption. Then you can show that this limit here exists. Remember that these sums are always well defined. I'm summating over the real numbers, okay? It looks weird, but remember that a only exists outside, only exists in a set which is enumerable. So these sums are always well defined because is absolutely summable over this set. So this limit exists, converges, defines the function in the upper half plane. If you translate the function a little bit up, it is almost periodic in the sense I defined before. And you have some decay condition, which essentially means that if you expand the Fourier, the almost periodic function into Fourier coefficients, into the Fourier series, the coefficients are have exponential decay. So this sort of translates to exponential growth of A. And if you take E of F, that is bounded type, and this limit here exists in 0. Okay? So far what I said was if you have mu and A real antipode Fs pair, all these four are satisfied. Okay? Then it comes the converse. Suppose I give you a function f, any one, any function, holomorphic, such that 2 works, 3 works, and 4 works. Okay? So that is 2, 3, and 4. Then I can define this quantity here, and it will be independent of y greater than c for some c. So as long as y is big enough, this always gives the same number. And it vanishes when lambda is less than 0, and defines a function. So now this defines lambda for any real. This defines a function, which vanishes for lambda less than 0. And that function is locally summable. Okay? And it has exponential growth. Okay? Moreover, you can find a measure that satisfies this identity. It's unique defined by this function. And moreover, if we let A be defined using this guy, so you sort of antipodally symmetrize E of F, and at 0 you have just to take twice the real part, then you just found the real antipodal Fs pair, and the identity 2, which is this guy, holds. Okay, which means that you complete the circle. If Fs pair has to be built from a function like that, and there is no other alternative. Okay. Actually, in the converse part, you can even make a weaker condition. Actually, you could even go here and make a slightly weaker condition on condition 3, and you can still come back. Okay, but I won't state that result. Okay, so this gives a complete characterization of the first question: what kinds of measures, measures with pure point and pre-point support and spectrum exist. I'm doing even more. Now you can assume that mu is any measure. And that the right-hand side is pure point. As long as the right-hand side is pure point, you can classify things that, anything like this, essentially. Okay? And in the other lectures, I will sort of try to make particular cases of this theorem, especially one which will be more relevant to physics. And then you can further classify these pairs in the lines of these two results. Okay? Here, Q will be just any trigonometric polynomial. The classification I will arrive is a bit more general, and you could allow actually to put Q here and another polynomial here if you like. Okay? And you can classify, there will be a classification result for those very similar to this. Okay? But in that case, again, it would be for locally finite support, locally finite spectrum. But there are other results that don't assume locally finiteness that I will show as well, which are applications of this main result here. Okay? So, so that's it for today. Okay, thank you.
Question, comments? Thanks, Felipe. Again.
Thank you.
Thank you. So next time is going to be Friday, Auditório I,
Friday, yes,
and 3:30 p.m.
3:30, yes.